All right, great. So I just want to introduce Judy Hoffman, who's an assistant professor in the School of Interactive Computing at Georgia Tech and a member of the Machine Learning Center. She received a PhD in electrical engineering and computer science at UC Berkeley in 2016 and has been a postdoc at Stanford and UC Berkeley. She's explored computer vision and machine learning with specialization in domain adaptation, transfer learning, and algorithmic fairness. She's received a number of awards, including NSF Graduate Fellowship, an AI Minor Top 100 Most Influential Scholars in Machine Learning, and an NVIDIA Female Leader in Computer Vision Award in 2020. So with that, I would like everyone to warm welcome to Judy.
Thanks, Keith. Yeah, it's a pleasure to be here today. And oh, hello?
Yes, I'm still here.
Oh, that's so weird. My account says that it's signing me out. I might get kicked out for just a second and then I have to log back in. Sorry about this.
Oh no, all right.
Well, maybe it won't happen. Can you all still see my slides and everything?
We see now we see your slides. Before we briefly saw your background, your desktop.
Okay, well, hopefully that doesn't happen again. That was very strange. All right, anyway, like I was saying, it's a pleasure to be here. I'm going to be talking today about understanding and mitigating model and dataset bias. A lot of what I'm going to talk about is going to focus on computer vision, but it's broadly applicable to other areas of machine learning. And really what I want to think about are ways in which we can design algorithms to help mitigate when you do find out that there's bias either in your data set or inductive biases in the model. But also, how can we design visualization tools or discovery tools in order to better understand what is causing such bias? So to get started, let's just take a step back and think about what's the standard conventional wisdom in computer vision and more broadly in machine learning these days. And the conventional wisdom is that if you have enough annotated data examples, and you have a high capacity deep learning model or an end-to-end learnable function, then you're sort of have a simple recipe for a successful predictive learning model. And the way that we convince ourselves that this is true is we tend to design standard recognition settings in the computer vision space. We design standard benchmark protocols where what we do is we collect a large data set, we accumulate some annotations, we train our model, and then we validate our model. And today's talk is going to focus on this last piece here of what does it mean to validate a model? What does it mean to determine that you assume this model performs as well as you expect it to perform? So one such way that we do that is to design benchmark tasks. Benchmark task in vision might be something like this ImageNet dataset, which has millions of images and asks you to be able to predict whether an image is from one of 1,000 potential categories. Performance here is measured in accuracy, and on the x-axis of this graph shows performance over time. So what you'll see is that as we introduced these end-to-end learned models, as we gave them more and more parameters to learn with and used faster and faster computational platforms, we're able to improve performance on this benchmark task. And this will give you the feeling that for a classification problem such as this, we're sort of in a regime where we can get a very solid solution just by taking this large annotated data set, placing it together with our deep learning models. And we make that assumption based off of our performance on this held out test set from within the ImageNet data set. So to understand why this way of measuring overall performance might be limited, let's start by thinking about this last model here that I've circled in green. This model is probably some large ResNet trained with all the bells and whistles to perform well on this ImageNet dataset. ImageNet contains lots of categories, including categories like how to recognize dogs. So let's imagine we take this model that works really, really well on this ImageNet dataset and see what happens if we try to recognize a dog in a YouTube video. So this is a video of a dog just running. Somebody found it interesting. They wanted to share it with others, probably a pet. The problem is that that model that worked really well at recognizing dogs in still images failed to recognize the dog in this video. And the question is, why is there such a huge mismatch between how well a model appeared to perform on a held out test set versus how well it performs on another data regime where we as people would assume it should translate well? And this has to do with dataset bias. So here I'm showing you a sample of images taken from the ImageNet dataset that are labeled as dog. And ImageNet was collected by scraping social media sharing sites. Flickr was one of the really popular ones at the time that they scraped. And there is an implicit curation bias in terms of what people want to share on some of these sites. So if you're taking a photo of a dog, and you want to upload it and share it with family and friends, you're probably going to take care and make sure that your photo has nice photographic qualities. It might mean that it has nice lighting conditions, the subject is in the center of the frame. In the case of dogs, probably the face is going to be visible because we find that to be more interesting. But all of these biases that exist in kind of that still frame medium may not persist even when you shift just to video. So if we look at some of the still frames that are available in the video, we'll see that you very likely have lower resolution because you need to share lots and lots of frames to make the video. You're going to have action, which means that there's motion blur. And you're going to see the dog, in this case, in a wider variety of poses than you would have seen in the original database. So nobody would take any of these still frames, especially not the last one, and say, hey, this is a great photo, I'm going to upload it to Flickr. The reason why it persists in the video domain was because you captured an action that you thought was cute or interesting and you wanted to share it with people. And because of that, you're going to have just wider variation than you would have had in the still images. So this small difference between how people choose to capture information can have a huge impact in terms of what the model learns. And a lot of my past work has focused on ways in which we can mitigate some of this inherent bias using a technique called domain adaptation. And this technique assumes that you have a set of predictive functions, maybe categories that you would like to recognize. And the issue is that the area in which you have lots and lots of labeled examples of those categories doesn't match the type of data that you would like to, at test time, use your model to predict on. So we have what's called our source domain and our target domain. Source domain has lots of labels. Maybe this is your curated data set like ImageNet. Maybe you're trying to recognize products, and so you have a product warehouse, stock images of photos all in white backgrounds, or maybe you're simulating your data. So in the bottom left corner, we have example images taken from a self-driving simulator. And these are areas where you either have or it's easy to acquire lots of labels. So you can use the power of supervised learning in order to train a model that performs well. Problem, of course, is that it performs well in this source domain. We'd like to make sure that it performs well in the target domain. And the target domain might be the way the objects appear in the wild. So you're trying to recognize a particular backpack, a particular bike. You have a stock photo. You'd like to recognize the way that it appeared when somebody snapped a photo with their phone. Or you're trying to generalize the simulated data to work well in the real world. So I'm not going to go into too much of the technical details of this style of approach. It's been around for a few years, but a really popular style approach that I've worked on in the past is called domain adversarial adaptation. If you're at all familiar with GANs, it has a very similar flavor. The intuition, though, is that what we're trying to do here is we have one set of data with lots of labels. We can train a classifier. That's the red branch at the top. Now we have an unlabeled set of data where we would like our model to be able to perform well on. So what we're going to do is we're going to model the representation distribution of both the source and target data. And we're simply going to ask that these two distributions are aligned. That's the high level goal. And the way that we implement that is we start out by training a domain classifier. So the job of this piece of the model is to be able to see whether or not we can distinguish a feature from the source or the target. And intuitively, if you can distinguish between these two collections of features, well, that means that they're kind of misaligned, they're far apart. So we want to alternate between learning the best domain classifier and updating the underlying representation so as to confuse this classifier. So eventually, if we have aligned representations, it should be impossible to distinguish between the two. And that will lead us to what we'll call a domain invariant representation. So we can take this style of approach, we can apply it anywhere in the deep learning hierarchy. You can apply it directly in pixels. You can apply it all the way towards the output in what we'll call latent space. And they are actually complementary to apply at different levels. And we had one approach in 2018 called Cicada, where we applied both all the way close to the input at pixels and all the way close to the output at softmax predictive values. And we can apply it to classification or other vision tasks like what's shown here, semantic segmentation. Semantic segmentation is the task of being able to label with a particular semantics like car, road, every pixel in the image. So on the left, we have an example self-driving image, and on the right, we have an example predictive output. And these types of annotations are really expensive to collect. For this data set that I'm showing here, it costs between $10 and $12 per single frame to get these types of pixel-wise annotations. And unfortunately, for an application like self-driving, you really need a lot of experience in order to become proficient in this domain. You need to have experience across things like different cities, what type of car was it captured on, what sensors were used, what were the weather conditions, time of day, things like that. So you can imagine that getting all of that diversity of data may be intractable. And so what a lot of people have considered is, can we just simulate a lot of these situations that we maybe don't have perfect examples for, and instead just transfer or adapt our model from simulation to real world? So that's what we're going to do here. We're going to use the domain adversarial learning to transfer from Grand Theft Auto images that are synthetic to this cityscapes driving data set. And the first thing to do is to perform adaptation close to pixel level. What this will do is this will take a source image, our synthetic images, and make them appear more realistic. So this is our original input image, and after we do the transfer, we get this output image. So the main changes that are easy to notice just in a talk like this have to do with the road. So I'll show you again the original image. This is emulating actually close to where you guys are in the LA area. And you'll notice that the road is a little bit patchy and has a yellow center line. And after adaptation, the road is now monotone, more or less, very smooth, and has a white center line. So these differences maybe seem trivial to people, but have huge impact on the ability of the model to actually recognize the road as it appears in the real images. So we can do this across a wide variety of images, generate for ourselves a more realistic set with which we can train our supervised model. And then we can further do adaptation in the latent space in order to refine our representation. And once we do that, we can evaluate our performance on held out images from the real world. So in the upper left, we have a cityscapes image, and upper right shows you what is the desired output of the model. Bottom left is before adaptation, meaning this is the output that a model would give you if you just trained in simulation and did nothing to adapt. And then in the bottom right, we have the improvements in terms of your predictive output without access to any real world annotations, just by doing these statistical alignment techniques. And you'll notice that aside from the road improvements, you also find things like this extra pedestrian or this street sign in the background.
May I interrupt briefly? I was curious though, how does the simulation know what is, how do you know in the simulation what is a sign, what is a street, etc., without human annotation?
Well, because they're generated, so you build a model of a sign and then you generate the pixels corresponding to the projection of that model into the scene. So it's kind of implicit in the generation process.
I see, I see. So it's not just looking at the game, it's actually that you know in the game, you know based on maybe from the code itself in the game what is a sign, what is a street, etc.
Right, right. And more broadly, the idea would be that you build a simulator for the task that you care about. You generate images, and then obviously when you generate, you know, your code knows what you used in order to generate it.
Okay, thank you.
Sure. Any other questions? Okay, so that's standard adaptation. And to summarize, just the problem statement of general adaptation is that you have this initial model, you have lots of labels, you can train supervised fashion. It seems like it performs well when you evaluate on held out source data, but it doesn't perform well in this related target domain where you'd actually like to deploy your model. So we're going to use either unsupervised or semi-supervised adaptation techniques to modify that original model slightly in order to better specialize it to this new setting. But a natural question to ask is, was there anything that we could do during that initial training phase in order to produce a model that was less susceptible to its own biases? If you could do that, well, then maybe you needed to expend less effort adapting to each new domain that you encountered, and instead have a slightly more general purpose model just from the get-go. So to study that problem, we set up this task. It's been studied in the literature under terminology called domain generalization, which satisfies, just as I was saying before, we want to be able to learn from a set of labeled data to produce a single model that is as general as possible, as domain invariant as possible, so that as we see new data over time, we know that we are kind of already starting off in a strong point of generalization. So this is not necessarily identical to supervised learning scenario where your task is actually to specialize to a particular domain that you're in right now. So we're trying to learn the pieces that persist across lots of different varieties of data. And a standard way in which prior work had looked at this problem was to say, okay, let's imagine we have a few different types of data, clip art, sketch, and paintings. What we can do is we can put them together and learn a shared model that can simultaneously extract relevant information from all of them. And then at test time, when we see a new domain, like this real image of a dog, well, we can just copy over that model and use it, and it'll work better out of the box because it already worked across 3 domains, so we should assume it'll work better on this 4th. The problem with this style of approach is that now you see yet another domain, this quick draw domain. Well, the strategy is exactly the same. You take that original model and you apply it to this quick draw data. And so what this implies is that you have the same model that's always applied to all different target domains. And while that's a good place to start, it over prioritizes invariance. So if there's information in a couple of your domains, like in clip art and painting, you have color, there's no color in Sketch. So if you needed to only extract information that persisted across all domains you've seen so far, well, then you would choose to ignore color in this case. Clearly, there is some information that might be useful for predictive performance in some of your domains. And we'd like to make sure that we can retain some of that information and reuse it when it applies in your novel domains. So at ECCV this year, we proposed a work called Domain Masks for Generalization, or DMG, where we tried to operationalize this intuition. So instead of having a shared representation across all domains, we're going to have a representation which allows for some domain-specific components, highlighted here with just the corresponding colors, some partially domain invariant. Maybe you have a feature like color in this case that persists across clip art and paintings. And then you maybe have a large portion of the representation space, which is in fact domain invariant. These are features that appear across all domains and are just generally useful. So then, of course, the idea is, what do we do at test time? Well, ideally at test time, when we saw this real example, we'd be able to use both the relevant domain-specific components as well as the domain invariant components in order to produce our final predictive model. And what components are domain-specific and relevant for this new domain may vary as you see different sorts of data at test time. So how can we learn to separate our representation in this way? This is how DMG works. We start with a collection of domains. We're going to learn a shared feature extractor as well as a domain mask. So we will learn a mask per domain that we have at training time. And what this mask is going to produce is a real valued or binary valued output. We've tried both. And that is then going to be combined on top of your current feature extractor to show you which portions of the feature space you should care about for this particular domain. And then subsequently, that will be put into your task network, like your classifier. And this will be the overall model. So how do we encourage these masks to have some balance between domain specificity and domain invariance? We do this by introducing an intersection over union loss, which just looks at a ratio of the overlap to all of the features that are cared about across any of the domains, and essentially asks for some amount of the features to be non-overlapping. Once we have one of these binary masks, it's applied very similar to the way dropout would be applied, except that we have learned the output per domain. So for each neuron, there's a mask parameter that just decides whether or not to turn it on or off based off of the domain label. And again, we introduce this soft IOU measure to encourage some amount of domain specificity. Actually, if you don't have this at all, if you just allow everything to learn simultaneously with no constraints, you will tend more towards domain invariance. And then at test time, if we know nothing about the domains that we have, a simple solution would just be to average across the masks. So we're going to show some evaluation on this standard benchmark called DomainNet. This data set has 6 different domains and actually 345 categories that I can't show all of them here, but here was just a random sampling. It's a pretty challenging data set, but the nice thing about it is that because it has multiple domains, it allows us to really study this problem of how well you can generalize. So the way that we are going to set up our experimental protocol is we're going to hold out one domain at a time. So we're going to train on 5 domains, test on the 6th, and do sort of a round robin, so that by the end of the day, we get an evaluation on each held out domain. And to not overwhelm you with lots and lots of numbers, I'm going to show just an average overall performance. And really the only takeaway to get from this that I want, or the point I want to make in this talk, is that there's a couple different things you can think about measuring. One of them is just how well do you perform at this pure generalization task? So how well you trained on 5 domains, you test on the 6th, how well does that model work? And kind of alternative formulations get around this performance across different architectures. Our model outperforms them at this generalization task. So that's good. That means that there's enough domain invariance in the model to be able to generalize to a new scenario. But at the same time, we also wanted to be able to understand how much predictive performance we retained in the original domains. So rather than only evaluating on generalization, we'd like to also understand how well we performed on those original 5 supervised domains. With the idea being that if you have lots of data and you train a big model, you probably don't want to keep around one specialized model to your original domain setting and then one generalization model. You'd like there to be a single model that performs well across all of these settings. So to study in-domain performance, we can again look at aggregate and multi-headed version baselines, as well as MetaReg, which was a NeurIPS paper on domain generalization. And if you know nothing about the source models and just do the same sort of mask averaging to evaluate your generalization model, you find that it works kind of comparably to the best baseline strategy here. But because we have a domain-specific mask, we can actually use domain information, if it's available, in order to select just the most salient mask to use. So without changing the parameters of the model, we're just selecting which mask to use, which features we've learned are relevant for this domain. And once we do that, we can improve performance further. So to summarize this section on mitigating domain bias, we talked about adaptation as a way to leverage some unlabeled data that might be available to you at test time in order to specialize your model to a new scenario. And most of this focuses on these type of statistical alignment techniques to encode domain invariance. Generalization is focusing on a different part of the pipeline, whereby you try to encode your original model to be as generalizable as possible, as useful for a variety of settings as possible. So between the two of them, you're going to start out with a general purpose model, and you'll be better equipped to specialize it to a new setting. Any questions up until this point? Okay, I'm going to move on to the next part then. And up until now, I focused on ways in which dataset bias might arrive kind of naturally or coincidentally. It wasn't that somebody intentionally collected still images with a center bias or with a face bias and intentionally shifted to this video domain where those biases don't exist. It just sort of happened, which means that sometimes the model trained on ImageNet may work on video, sometimes it won't. Now, a very related setting is when you actually are confronted with a malicious actor who is intentionally changing your target distribution. So you've trained a model, you think it works well, maybe you only ever expect this model to be evaluated in domain, but actually there are people who control what are the inputs to your system, and they may manipulate those inputs so as to degrade the performance of your model. So how can we study this problem, both in terms of mitigating biases, but especially in terms of being able to start to understand how biases are integrated into a model. So to get started, I'm not sure if people have seen this image before. I would expect a lot of you have, but adversarial examples in vision take a form that looks something like this. We have an original image, and there's an adversary who can choose to add some amount of small perturbations to the image. And they're going to be chosen a very particular way that may look like noise to people with this center image here. They're going to add them to the image with a really small magnitude so that the output image all the way on the right looks probably imperceptibly changed to people, but to an algorithm, it completely changes its output. Originally, your algorithm called it a panda. Now it calls it a gibbon, and it is very confident it is a gibbon, 99.3% confident. So the fact that these kind of small perturbations exist is interesting in and of itself, because it implies that there's some amount of learning happening in the model, some amount of either bias or unconstrained portions of the feature space, which can result in large predictive changes. So if we want to understand how can we make models that are more generalizable and more robust and less susceptible to biases, then it may be of value to study these adversarial cases. So the first thing we're going to look into is how can we even begin to understand an adversarial perturbation and what it does. So to do that, I'm going to introduce a visualization technique where we're going to start with just an input image. This is an image taken from a tiny data set called MNIST of handwritten digits. And these images are really little, so it makes it easy to do visualization stuff. And here we have a 0, 28 by 28 image. We can vectorize it. And then we can learn an orthonormal projection, or even just randomly pick an orthonormal projection to take this large vector and place it into 2D space that we're going to use for our visualization. Once it's in 2D space, we can now imagine sweeping over this projection space. So if it was a random projection, this just means you're adding random noise in different ways. If it was a learn projection space, like maybe projection according to adversarial directions, then you're kind of sweeping along the directions that an adversary would change. But each of these sweeps, each of these spots corresponds to some type of a perturbed image. And then we're going to imagine taking that perturbed image and placing it through our original model that was just trained on clean data. So once we do this, we can visualize how the output changes in response to input perturbations using these decision cells. So in this visual, what I have is the training point in the center of the frame. And again, it was projected using this 2D projection. We've swept across in order to evaluate all of these different images. And each image is going to have its own predictive output, which is color-coded on the right-hand side. And what this tells us is it gives us a slice into the model's predictions. So first and foremost, this ball that I've drawn here indicates kind of a buffer radius around this data point before which you start misclassifying it. So if I were to move along the direction of the black arrow, then I'd be able to, with this radius or this amount of perturbation, change its prediction to a 2 instead of a 0. Some other high-level qualities to notice is the fact that these decision boundaries are non-smooth. And of course, it's hard to tell just from one image, but in general, this is a pretty small radius around this image, meaning that you don't need to add a lot of perturbations in order to start misclassifying. Some other techniques that people use, like standard techniques that people use for generalization regularization, are things like weight decay or L2 regularization. And this leads to a decision boundary shown here, where the boundaries are very smooth, but this the amount of perturbation that you would need to add in order to misclassify an image is still pretty small.
I have a question. I'm sorry.
Yeah.
So I'm wondering, so this is done on the input space, but I'm wondering if you have done such an analysis on the latent space as well, or like kind of aligning those two together to see what is the relationship.
Yeah, so this is perturbations all the way on the input space and monitoring resulting perturbations all the way on the output space. We haven't done this type of analysis doing any of the other combinations. I mean, you could imagine studying changes from an input, intermediate input all the way to the output, or even just from intermediate to intermediate or from input to intermediate. But we haven't studied that.
Right, because I have previously done an analysis, and it seems like whatever is happening in the between or in latent space is totally different than the input space. So it was kind of interesting to me, and I was wondering if you have seen such a case in your analysis, if you have ever done it.
So we didn't in this project purely because we were studying these adversarial example cases, which are by definition done in the input space, because it's assumed that your attacker only can manipulate what they give to you. And in many cases, they may not have access to your model at all. They just put an input in, get an output out. But I think it could be interesting from a number of different perspectives, not least of which just understanding models better.
Yes, thank you.
Sure. So through these types of visualizations, we started thinking about just the notion of input-output variation. So we have this initial model, we trained it, it seems like it works well. And really the property that we're sort of looking at in those decision cells is how much does the output change in response to an input change? And like that discussion we were just having, of course, you can monitor, you can define input and output however you want. In this paper, what we did was we defined it, of course, as the input pixel change and how much of an output predictive change it results in. So the intuition here is that if we compute this Jacobian matrix, and we're just going to be measuring how much does the output deviate in response to an input deviation. And if we want to make sure that we add some stability to the model in response to input perturbations, well, what we can try is just minimizing the Frobenius norm of this Jacobian matrix. And once we do that, we can visualize our decision cells for this Jacobian regularization model. And the biggest change that you notice is the fact that this radius has enlarged. And that's just by virtue of the fact that that's explicitly what we asked the model to optimize. And so this gives us some more of a buffer around each data point. So you have to add a larger perturbation before you can successfully manipulate the predicted output. So it's worth noting that this technique is just a general robustness technique. I'm going to show results on the next slide for adversarial attacks. But most adversarial attacks actually operate by mimicking an attack and training a model explicitly on attacked images. In this case, this is not specific to an attack. In fact, if it was specific to any attack, maybe it would be most tuned to like Gaussian noise or something like that. But in general, it's just this input-output variation. So anyway, on this MNIST data set, we can compare the performance across an attack. So on the x-axis, we have this PGD iterations. As you go further and further to the right, the attack gets stronger and stronger. So all the way on the left would be like an unattacked image. All the models perform comparably on the original unattacked images. And then what you ideally would want is that as you attack them with stronger and stronger attacks, you still retain that high level of performance. And what you'll see is that the Jacobian regularization or the combination of Jacobian regularization with adversarial training does a good job at that. The other thing I want to point out about attacks and defenses in general is that when people start developing defense techniques, oftentimes performance is, again, going back to that first slide about how do we validate our models. So if our idea in adversarial attacks is that we want to evaluate our robustness. Well, what most of the community would do is that they'll have an attack benchmark and evaluate your corruptions, your performance against the corruptions. But maybe at the same time, especially in the attack case, if you develop a model, you want it to be robust to attacks, but you really would like it to perform well on the original data. Hopefully, you are not only defending against attacks, you're also actually just like doing your job of whatever the model was trained for. And what we observed in this project was that as we increased the regularization parameter, or more broadly, as you strengthen your defense, you do increase your robustness, but at the cost of a drop in your performance on the original data. This is sort of undesirable. It's actually a phenomenon that's been observed multiple times in different papers, including this recent paper that studies just this phenomenon. So what we thought about was, is there a way in which we can update some of these defense techniques, adversarial training being the most widely used backbone of defense techniques? Can we update it in order to improve this robustness accuracy trade-off curve? So adversarial training, for those who aren't familiar, works like this. You have your original supervised model that's been trained. You freeze it and you consider, if it's a gradient-based training solution, you consider taking a gradient with respect to the original loss and mapping it all the way back to the input space. So in this case, it will give us some sort of gradient image that we can then apply with some scale factor to the original image in order to produce our adversarial image. And then adversarial training is simply the process of computing these for all of your training images and training a new model using these adversarial images. So it's a pretty standard learning strategy, and it works decently well. People have added lots of different further modifications to that core algorithm to improve performance even further. But the one detail that persists is the fact that most of the time, all images are treated equally. And what I mean by that is that when you're generating an adversarial image, you always you're computing these gradients, and then you're adding with the same perturbation ball, same scale parameter, you're adding that into the training image. And so our hypothesis was that asking for the same amount of defense robustness on every image may lead to a drop in your clean performance. And to understand that, we can visualize this example shown here. On the left, I show an image of a bird where, with a tiny epsilon, a tiny little change to the image, magnitude change, you can already manipulate the model to call it a deer. And usually the size of the perturbation that would be added to an image like this would be 16. In this case, you only need to add a perturbation of 1.5 in order to flip the predictive output. Now, on the other hand, we have an image of a deer on the right-hand side, where if you add a perturbation ball of 16, you're still going to call it a deer. It doesn't confuse the model. You actually need to add a perturbation up to 28 before you start confusing the model. So what this tells us is that there are some images that are easier to confuse than others. And maybe instead of training for robustness with the same parameters on every image, there could be some sort of instance adaptive technique. So that's what we did in this paper, was instead of using the standard adversarial training where you have a single epsilon, a single scale parameter for every image, we're just going to update in order to have an instance specific scale parameter. And you can check out the paper if you're interested. There's a whole bunch of examples of both the images that we found that are easy to confuse and the ones that are hard to confuse. Hard to confuse usually are more canonical looking images. And once we do that, we can evaluate our overall performance using this trade-off mindset. So on the y-axis, we're measuring how well does our model perform on unperturbed data, just the normal test set. And on the x-axis, we're looking at the robustness of the model. So how well does it perform against an attack? And ideally, you would have a model that's in the upper right corner. You'd have a model that performs equivalently well on unperturbed images and is robust against attacks. But of course, there's usually a trade-off. And if you use standard adversarial training with a fixed epsilon ball, even if you change what is the size of that epsilon ball, you experience the trade-off curve that's shown through these blue dots. So if you train everything with a really small epsilon ball, well, you retain your clean performance, but you don't really induce any robustness. And as you increase the size of that ball, you improve your robustness, but take a huge hit in terms of your natural accuracy, your clean accuracy. And so in this paper, what we were trying to do was kind of break away from this Pareto curve and increase the trade-off between robustness and accuracy. And those are shown in red. So this is the end of the adversarial robustness section. And, or rather the adversarial defense section. I wanna pivot back to thinking about understanding model bias using these adversarial attacks. So we saw before that the decision cells, looking at input manipulations and how it affects output predictions, is one way to consider this. Another way in which we've thought about it recently has to do with emulating the likelihood of a sample under a given model. So rather than what is it predicting, I just want to understand, is the model sort of, do we believe it's equipped to handle this particular data point? And the challenge here is that most models have been trained discriminatively, which means that you have this logit as an output, but you don't necessarily have the generative model. Fortunately, there was a recent paper that did some mathematical tricks and showed that you can take these discriminative outputs and emulate using basically just Bayes rule type techniques. You can then emulate the joint distribution. Of course, you will not have access to this normalization factor Z of theta. It can be quite computationally intensive to even estimate it, or even intractable in some cases. So we'd like to avoid that, especially because we are trying to do this for a visualization technique. And so we don't want anything to be overly computationally intensive. And what we came up with was the fact that we wanted to be able to understand how the likelihood changes in response to input deviations. So instead of just having a marginal log likelihood where we have this pesky Z of theta, instead we can look at a difference between the log likelihood of, let's say, the original image and a perturbed image. And once we do that, we can now produce a visualization like this, where again, we're projecting into two different random directions, but now instead of measuring how the output prediction changes, we're measuring how the model's likelihood of this sample changes. So what this means is that, and again, the goal here is that we're trying to understand what causes a model's prediction to fail. So if a sample is really likely under our current model, then maybe we feel like the result is more trustworthy. And we can do this across a variety of models, both the standard training model in the upper left, where you'll see it's a super peaky distribution, meaning that as you induce variations to the input, the likelihood of that sample drops off pretty quickly. And in adversarial training, you see something really different, which is that this likelihood becomes much flatter. So the perturbed samples are sort of getting close to the likelihood of the original sample. And this maybe starts to give us some intuition as to how these defenses are allowing us to improve the predictive performance on these perturbed samples. think in the interest of time, I'm going to skip some of the details and evaluations on this visualization technique, but the code is available for it if you're interested, as well as the paper is online. And we have, I'll just say that we have some quantitative measures that can help you to determine, based off of the area under these relative likelihood curves, how robust you would expect your model to be. So this section of the talk focused a lot on understanding how bias introduces itself and causes deviations with predictive outputs as inputs change. And we do this by viewing this adversarial scenario, both in terms of monitoring the adversarial scenario directly using these decision cells, monitoring how minor regularization parameters or different training techniques for robustness might help us to improve the model's predictive performance as we have different input-based deviations. We talked about how robustness may not be a one-size-fit-all idea. This is a very similar in flavor idea to the DMG results, where we were basically saying, like, you may not want to have just an objective of pure robustness or pure generalization. You may want to allow for some sort of domain specificity or some sort of instance specificity in this case, as a way to trade off between in and out of domain performance or clean and robust performance. And then finally, the relative likelihood landscapes is a new line of work that we just showed at ECCV this year. And I think there's a lot more to study in that framework. So in the last couple minutes of this talk, I want to just mention a little bit about bias more broadly. In today's talk, I focused on two types of bias, one being what people will call dataset or domain bias. And again, these are where the bias happens just because the world changes, or it's just coincidence. There's some reason why people capture data in a different way. In the adversarial case, there was something malicious that happened in order to manipulate the images, and that causes the model to degrade. But in general, the data sets themselves oftentimes have an inherent bias to them, which may even mimic the test time bias, but may not truly represent the world that we would like to deploy our models in. And so to think about that, we just want to understand one flavor of what I mean, one flavor of the repercussions of just accepting that dataset bias exists and training models with a biased dataset. So to do that, we're going to think about this self-driving domain again. And here I'm just showing you some video, example images driving around. There's all kinds of deviations people pay attention to. They try to have different times of day, different weather patterns, whether or not you're on the highway or in a city. And so, these are the kind of things, these are the types of variations that people pay a lot of attention to and trying to make sure they have examples of. But what people pay less attention to are things like predictive bias on certain subpopulations. And this was work done in collaboration with Jamie Morgenstern, who's now at UW, where we tried to ask the question of how well do these models that maybe appear to perform pretty well at doing things like pedestrian detection, how well do they perform at different subpopulations? So following the gender shade style of work, we looked at Fitzpatrick skin type labeling, where you asked Turk annotators to be able to specify whether or not a particular pedestrian had different skin types. Or maybe in some cases, actually in the pedestrian case, a lot of them you just can't tell. But in some cases you can tell, and we were able to get annotations so that we could measure performance across different skin types. And The first thing that we observed is that in a lot of these benchmark data sets, there's a significant underrepresentation of different skin types. Here I have a chart showing both train and val breakdown of lighter skin and darker skin individuals. And what you'll notice is that there are substantially more lighter skinned individuals represented in this data set. So of course, the natural question is, well, does this sort of bias actually impact anything? And so we can measure performance and find that there is actually a measurable and somewhat significant drop in performance between these two populations. But I'll just note that there's kind of an implicit challenge here that with only 100 samples of darker skinned individuals in the val set, it's sort of impossible to even make really true statistical claims. So we're kind of at this stage where we have so few samples that we can't even measure how biased we are. Natural questions to ask here are, why do we have this performance drop? Is it just purely lack of training data? Are there simple things that we can do from standard like long-tailed learning techniques, reweighting? We tried some of these things in this scenario and didn't have great improvements. There might be confounding factors here, and we tried to control for things like times of day and occlusion and didn't see that any of that had major impact. So this leaves us in a state where we have a bunch of challenges that need to be addressed. The first is that if we want to be able to understand this type of bias, it requires a lot of manual annotations. It requires manual definitions of the kind of bias that you would like to annotate. And that's time consuming and costly for every sort of audit that you might want to do. And there's also a challenge in being able to understand where the bias actually comes from. Is it from the data or is it something inductive in the model itself? I mentioned before that in order to answer some of these questions, we really need to have more data just to be able to have statistically significant claims. There's a question of how should you mitigate? I showed you examples today of domain adaptation, which is one way to mitigate coincidental bias. But it's, and people have tried those kind of techniques in the algorithmic fairness literature, but it remains unclear if that's the best solution in this case. So I'm going to conclude by just stating that in my worldview, these three topics that I've talked about today, domain adaptation, adversarial robustness, and algorithmic bias, are very, very connected. They all deal with different forms of either data set or model bias. Adaptation heavily focuses on mitigation, or usually in the form of domain invariance. Robustness focuses on being able to do some sort of generalization to these different perturbations. And algorithmic bias is trying to be able to, at the very beginning, even just understand what are the biases in the data or in the model. So with that, I'm just going to thank my collaborators. I had many collaborators on these projects, both students at Georgia Tech, colleagues from FAIR, UMD, and DIFIO. And if there's time left, I can take some questions now.
Great, thank you so much, Judy. We might be out of time, so maybe only one question. Does anyone have a question to ask her? All right, I'll just ask one very brief question. Let's see. When you were mentioning the way in which your models can be better at adversarial attacks, the question that I was thinking of is, does that mean it's also better for generalization more generally? Is it able to work well in sort of out-of-domain data sets or out-of-sample data?
Yeah, I think that's the eventual goal, is to really bridge those two scenarios. We tried it, I think only in the digit scenario, and didn't see much success there. But some of these data sets or some of the way that these data sets are constructed is very toy. So where we saw improvements was over corruption data sets. So there's I don't know if any of you are familiar, there's a data set called CFAR and ImageNet corruptions, where you deal with things like whether or not there was motion blur, or whether or not there was some sort of pixelation, or they're trying, contrast changes or emulating fog in an image, things like that. And it helped a lot there. But in terms of translating between cartoon and real, I'm not sure if it will necessarily help with that type of scenario.
Okay, great. Thank you. So with that, I would like everyone to thank Judy for this really excellent talk. And I believe you'll be seeing a couple people later in the afternoon, including myself.
Yep.
All right.
Sounds great.
All right.
Thanks,
See you.
everybody.
You can stop the talk now, Amy, or stop recording, please.